today we will discuss similar voids, interstitial voids in BCC crystal, but we will see that in BCC crystal these voids have slightly different geometry. So, let us look at the BCC crystal. If you recall BCC crystal, any crystal is lattice plus motif. So, in particular BCC crystal has a BCC lattice and the motif is of one atom. So, one atom motif located exactly at each lattice point. So, the location is 000, which if you recall means at the lattice point, no displacement with respect to the lattice point. So, if we try to draw such a unit cell, let us draw a cube. So, this is the cubic unit cell of the BCC lattice and the lattice points are, since we are calling it body centered cubic. So, lattice points obviously will be at corners. So, each corner is a lattice point, each corner is a lattice point, as well as there is a lattice point exactly at the center of the cube. So, this is the lattice, and if I now add atoms, because I have to add. So, this is just a lattice, not yet the crystal. The BCC crystal will be when I add to the lattice one atom motif sitting at each lattice point. So, I add an atom at each lattice point. At each lattice point. One more important thing to note in this is that in this drawing I have drawn the atoms well separated, but in most real BCC crystal the central atom is closest to all the 8 corner atoms and it is assumed that they are in contact. So, the center atom and the corner atom are in contact. Which means, if they are in contact, if I draw them touching. So, this distance half body diagonal should be equal to the diameter of the atom. Is equal to atom diameter. So, if the edge of the cube, the lattice parameter is A, we know that the body diagonal will be root 3 times A. So, half body diagonal will be root 3 A by 2 and the atom diameter is 2 times the radius of the atom 2 r. So, we have a relation, we can write the lattice parameter in terms of radius or vice versa. So, we can write the lattice parameter as 4 r by root 3. We will need this relation when we are trying to do the calculation of size of voids in the crystal. Now, what kind of voids are there in this BCC crystal? We saw that in close packed structure we had tetrahedral and octahedral void. Similarly, here also we have tetrahedral tetrahedral void, and octahedral void. Although there will be some differences which we will see as we go along. So, the question is, where is the tetrahedral void and octahedral void located in this structure? Unlike what we tried to see tetrahedral and octahedral void in cubic closed packed structure, and we were able to identify these voids within one unit cell itself. But in body centered cubic, this is not possible. To identify the voids, to locate the voids, we have to look at least 2 unit cells, 2 adjacent unit cells. So, let me try to draw an adjacent unit cell to this given unit cell. So, let me extend this diagram by adding one more unit cell. So, I have just drawn a unit cell next to my starting unit cell with a common face. So, the middle face is shared between these two unit cells. So, this central face is shared. Now, we can identify the tetrahedral void as well as the octahedral void. Let us begin with the tetrahedral void. Remember, tetrahedral void requires 4 corners. So, we have to identify 4 atoms which form a tetrahedral void, and the way to do that now in this double unit cell is to 2 of the corners are the 2 body centers. So, I shade them red, so that to identify that now they are becoming corners of the tetrahedral void, and other 2 are on the shared face. There are 4 edges. You can take any of these these 4 edges. So, I take the top edge. So, 2 corners come from this top edge. So, if I join them now, so I join the body centers, and then I join the body center with the corners. So, you can now imagine a tetrahedron made out of these 4 corners. So, it has 4 corners, 4 faces and 6 edges. But if you look at the geometry carefully, you will find that one of the edge, or rather 2 of the edges. So, for example, this bottom edge, distance from the one body center to another body center will be same as the distance between the corners of the cube. That distance corner to corner is the same as body center to body center. So, this side of the tetrahedron is A, and this of course, the top edge is just A. So, this is also A, but the other 4 edges, if you look, are of a different length, because they are all these 4 are from the body center to corner. So, they are half the body diagonal. So, these edges are root 3 A by 2. All these 4 edges are root 3 A by 2. So, unlike the tetrahedron which we had met in the cubic closed packed structure, where all edges were equal and all faces were equilateral triangles, here edges are of different lengths and faces are not equilateral triangle. So, the tetrahedral void is not regular. Void, let us write it down in BCC is not regular, because faces not equilateral triangles, or equivalently we could have said edges not all equal. So, tetrahedral void in BCC, unlike the tetrahedral void in closed packed structure, is not a regular tetrahedron. The other thing which we want to do is to locate the centroid of this tetrahedron. The centroid actually gives the location of the void. Void is of course a 3D solid, so it occupies a volume, but the location of the void is usually given by the location of its centroid. So, let us try to do that. Maybe we will do this in this new figure. So, here to locate the centroid, let us do it in a way in parts. So, first we locate the centroid of these two atoms which are forming the body center. So, the centroid of these two atoms will be right in between these two, and that will be coming at the face center here. Similarly, we can find the centroids of the upper two atoms which is forming the edge. So, it will be at the edge center. So, then obviously, the centroid of all four atoms will be midpoint of these 2 points which we have identified, the face center and the edge center. The centroid of the tetrahedron is located here, which is midpoint of the face center and edge center on any given face. So, we can say that the tetrahedron is located on the faces at locations with the centroid located at as midpoint of face center and edge center. But one face of course has 4 edges. So, you can go in all those 4 directions. So, you will have on one face you have 4 tetrahedral voids located at such locations. So, you can count the number of tetrahedral voids per unit cell. We have 4 voids on each face and there are 6 faces. So, we can say 6 into 4. But each void you can see the void which we have drawn is shared between 2 cubes. Similarly, the other voids which we have not drawn will also all be shared by 2 cubes. So, we have to divide this number by half. So, 6 because of the faces, 6 faces of the cube, and 2 because shared by 2 cubes. So, you have 12, it is a rather large number. So, you have 12 tetrahedral voids per unit cell, and if you recognize that there are 2 atoms per cell, you can convert this number into 6 tetrahedral void per atom. Recall in cubic closed packed we had got only 2 tetrahedral voids per atom. So, the number of tetrahedral voids in BCC is much more. Now, we should do the calculation like we did for the closed packed structure for the regular tetrahedral void. For this irregular tetrahedral void also we will like to find the largest atom which can be located at the centroid. What is the largest atom which can sit here at the centroid without disturbing the corner atoms? Now, obviously, that largest atom will be one which touches the corner atoms. Despite the irregularity, if you see, this centroid is located at equal distance to all the 4 corners. So, you can take its distance from any of the corner. So, let me take its distance from this body center. So, if I drop a perpendicular here, let me call this centroid C and this perpendicular point P and this body centered atom as B. So, I get a right angle triangle here. CPB, in which the distance, let us see, the distance CB is what we are interested in. CB is equal to distance from centroid of tetrahedral void to a corner. Let us call that distance D, and that distance from this triangle we can see will be square root of Cp square. It is a hypotenuse Cb. So, it will be Cp square plus Bp square square root. So, if we continue our calculation, D will be Cp, you can see is 1/4 of A, because it was half of distance from center to center of the face to the edge center. So, it is half of A by 2. So, that is A by 4. So, we have A by 4 square, and Pb is half the edge length, because it is distance from the center of the cube to the face center. So, if you work this out, you will find A square by 16 A by 4, which will come out to be root 5 by 4 A. And if you use the relationship between A and R, you can write this as root 5 by 4 into 4 R by root 3. So, you get D is equal to root 5 by root 3 R. Now, you can see that this same distance will be the sum of the radius of atom which will be sitting at the centroid, the interstitial atoms, which let us call that R t, and the radius of the atom which is forming the void, which we have already called R. So, D will, which we have calculated as root 5 by root 3 R, is also equal to radius of the largest atom sitting in the tetrahedral void plus the radius of the atom forming the void. This quickly gives you an estimate of the radius of the tetrahedral void, or the largest atom fitting in the void, as root 5 by root 3 minus 1 times R. And and if you calculate it numerically, you will get something like 0.29 r. So, that is the, so we have calculated the size of the void, tetrahedral void, and we have also found the number of the tetrahedral void per atom and per cell in the crystal. This is slightly larger, you can see, remember for for cubic close packed or hexagonal close packed. So, for close packed structure, for close packed, the value of R t was 0.25, 0.225, sorry. So, around 22%. So, it is slightly larger, 29% of the larger radius. Now, let us look at the octahedral void. You recall octahedral void was formed by 6 corners. Octahedron requires, although octahedron has 8 faces, but it has 6 corners. So, where can I identify those 6 corners in this structure to form my octahedral void? Again we start with our 2 body centers as 2 of the corners, and the other 4 corners are all the 4 corners of this central common face. So, we take 2 adjoining cube, we take all the 4 corners of the common face, and we take the 2 body centers. These 6 corners define for me a nice octahedron. So, let me try to create that octahedron by drawing the edges. So, now we have the nice octahedron outlined between 2 cubes. So, the centroid of this is not as difficult to find as it was for the case of tetrahedral void, is right there at the face center. So, that is the centroid. So, that is the location of the octahedral void. So, octahedral void is located at each face center, but if you look carefully, each edge is shared by 4 cubes. So, for example, for this bottom edge only 2 cubes are shown on the top, but there will be 2 cubes below also. Let me try to add them quickly. So, there will be 2 cubes below also. And there will be body centers of this cube. So, if I draw the body centers of this cube, and this cube, then you can see that these 4 body centers with a common edge. So, this bottom edge is the common edge around which there are 4 cubes. They also form a square face. The 4 body centers are forming a square face, and these 2 edge corners are now one in front of this square and one in the back of this square, and the geometry is exactly same as the octahedron outlined above. So, there is an octahedral void also located at the midpoints of each center, because now the centroid of this new octahedral void will be at the midpoint of each center. This means that we have octahedral void at the face centers and we have octahedral void at the edge centers. Let us note that. So, centroids of octahedral void located at face centers and edge centers. So, this can then help us in calculating the number of octahedral voids. So, number of voids per cell will be, since one is located at each face center and there are 6 faces. So, we get 6, but you can quickly see that these face centered ones are being shared by 2 cubes. So, we have the effective number per cell at 6 by 2. So, this is coming from faces, and then we also have these edge centers one, but the edge center one you are seeing is being shared by 4 cubes. So, part of this octahedral void which is located at the edge center will be belonging to each of these 4 cubes, and there are 12 edges in a cube. So, we have 12 each being shared by 4. So, we have 12 by 4. So, which gives us 3 plus 3 6 octahedral void per cell, and we have to just half it. So, 3 voids per atom, because there are 2 voids per cell. So, we can continue now with trying to find the largest sphere which will fit in the octahedral void. Also note, I forgot to emphasize this, that the octahedral void also is irregular. So, this octahedral void is just like the tetrahedral void was irregular, octahedral void is also irregular void, because here also edges are all not of equal length. So, this edge is of length a, whereas this edge is of length root 3 a by 2. But there is one more irregularity in the octahedral void which was not there in the tetrahedral void. In the tetrahedral void, the centroid was at equal distance from all the 4 corners. Even that fact is not true for the octahedral void here, because the distance from the centroid to one of these body center point is a by 2. This distance is a by 2, but the distance from the centroid to one of these corner atom, as you can see, this is half face diagonal. So, this is a by root 2. So, which means these 4 atoms are located further away than these 2 atoms. So, from the centroid all atoms are not at equal distance. So, obviously, the largest atom will be defined by those atoms which are nearby, that is at a distance a by 2 from the centroid, because if you think of an atom, a small atom here and then gradually growing, it will first touch the nearby atoms, and if it grows even further, then these nearby atoms will start getting disturbed. So, the largest atom which will fit in this void is defined by the nearby atoms, these 2 atoms, and so like we had in the case of tetrahedral void, we have this distance between the nearest atom, which in this case is simply A. You can see this at these two distance is simply A, and that is the shorter distance. So, that is A, and we have already worked out that in terms of radius, that is 4 r by root 3, and the same distance should be equal to the radius of two atoms, radius of the two atoms here, this plus this. So, we have 2 r plus the diameter of the central atom, which we are calling the radius of the atom fitting in the octahedral void R O. So, which means we can now quickly solve 2 R O. So, we can quickly solve this. So, we have R O plus R is 2 r by root 3, which gives us the octahedral void radius as R. If you then work it out numerically, this comes out to be only 0.15 r. I am putting an exclamation mark, because octahedral void, which was expected to be larger, which was larger in close packed structure, turns out to be smaller than the tetrahedral void in this case in the BCC. So, because R tetrahedral for BCC we just now saw was 0.29 r. So, this is about 30%, this is about 15%. So, tetrahedral void actually is 2 times larger, it can accommodate 2 times larger atoms than the octahedral void in case of BCC. But this surprise will become even deeper if we look at the geometry further. So, let us look at the octahedral void again. We have outlined the octahedral void between two unit cells. Now, the question is, where is the tetrahedral void? So, if we try to identify the tetrahedral void in the same two unit cells, remember we had joined these two atoms and then we had joined the atoms to the edges. So, these 4 atoms were defining my octahedral void, tetrahedral void. So, from this drawing you can clearly see that tetrahedral void is totally submerged or is a subset of the octahedral void. So, tetrahedral void, let me write that down. TH void is included inside the OH void. In fact, if you see carefully, see this tetrahedral void I formed with this edge and is totally inside this octahedral void, but there are 4 such edges and I will get one tetrahedral void from each of these edges. So, the octahedral void actually has 4 such tetrahedral void. So, the volume of octahedral void is 4 times the volume of the tetrahedral void. Still we found that the radius which the octahedral void can accommodate is only half of the radius which tetrahedral void can accommodate. This appears counterintuitive, but this is a result of the location of the centroids of the two voids. The octahedral void was located here, centroid, and if we place an atom here, these two atoms are quite nearby and they decide the size, and that is what gave us a smaller size. Whereas, the centroid of the octahedral void we saw was halfway between this center and the edge center. So, that was located slightly above, which made this distance larger. So, a larger atom could be fitted in the tetrahedral void as opposed to octahedral void, despite the fact that tetrahedral void is included in the octahedral void and the volume of octahedral void is 4 times the tetrahedral void. So, with this we end the discussion on voids.